Hello, I'm Osman Hamid, and I'm going to be presenting my part in the presentation with Nicole and Maria. I'm going to be presenting my 5 slides and the conclusion and references. So our topic is basically about biomedical transport and how that relates to skin grafts, specifically for burn victims, and how transport and specifically diffusion, for my part, is especially important when it comes to actually integrating skin grafts with a patient's skin. So my first slide is going to be talking a continuation from Maria and Nicole, and it's going to be talking about actually the requirements of transport in the scaffold designs. So when it comes to the factors of the transport, after implantation, a skin graft can immediately start to have limitations when it comes to the ability of its capability of transport compared to normal skin. So there's 5 main factors that we can focus on for now, but there's actually more, but these are the most essential. So number one being oxygen. So oxygen transport is fully diffusion, basically, almost everywhere in our body as well, especially within our lungs and in our respiratory system, and specifically with our tissue. It's extremely important. So this is a really big issue to address, and with skin grafts, it needs to be extremely well. Um, if cells are far from each other, and if the skin graft is not made properly, um, and if the distance for diffusion is more than 100 to 200 micrometers, then that can be too far for the diffusion to meet. Um, and it can be too far from a blood supply, and it can even cause the cells to have hypoxia. So this makes oxygen very critical. Another one is nutrients as well. Nutrients can be the glucose or the amino acids, and they rely heavily on diffusion as well, in the same way that, in a similar manner, that oxygen does. Um, Waste is another big one. You can't, you have to make sure that cells within the skin graft and within the surrounding tissue as well are not, are having full transport capabilities, or else they're not going to have enough time or enough diffusion to be able to get the toxins out of the cells. Another and the fourth one is moisture. Having too much moisture in one area and too little moisture in another area can cause a lot of damage, or it can cause a little too much inflammation. Or if you have too much moisture in one area of the skin graft, then it can be much more susceptible to infections. And the last one, the fifth one, is drug delivery. How capable is the skin graft of allowing for the transport of the actual medicine to get absorbed within the tissue? These are all really important things, because if there's poor diffusion, then that can also lead to another infection rate as well for the drug delivery. So, in the first few days post implantation of the scaffold, diffusion alone will decide if the graft is going to survive, because that's one of the most important things. So moisture transport and MVTR. So for this slide, I'm going to be talking about how moisture is not um, just something that can be considered on the side. It's one of the core parts of if a scaffold is going to be successful or not. So um, with MVTR, um, you need to make sure that the water vapor is just controlled enough that it's not too much and it's not too little as well. So MVTR being moisture vapor transmission rate. This is something that's very important with diffusion and something extremely important for the skin. So with uh, with this kind of thing, you have to look at the oxygen trade-off. So if you have excess moisture, then it can fill up the pores and it can fill up the spaces, and there's not going to be that much transport that's going to be capable past that. But this can also reduce the effect of the oxygen diffusion because of the scaffold. So you need to see what the trade-off is. There's also, of course, the increased infection rate as well. As I mentioned before as well, with overhydrated environments that can cause more bacterial growth. So having that MVTR control, having that balance is extremely important to make sure that the scaffold actually heals properly and it can actually be of use to the patient. So Here's just a case study that we can use. We can just take any example of a product of a bilayer scaffold. So let's say that we do have an actual product of an actual scaffold that's being used. So how would it work is that with the layers of it, the top layer, it would be mainly for regulating moisture loss, making sure the skin doesn't get too dry, making sure that the skin has enough moisture and enough biological capabilities to fight off whatever it needs to. So this is essentially just maintaining the proper MBTR levels. But the lower layer of the skin graft, you want to make sure that that actually allows for cell growth to happen. And if it's a good enough scaffold, then it can actually allow for more vascularization so that those blood vessels can come in so that the actual skin graft can actually start to integrate with the skin around it. Um, so for the just to tie this in with the theory behind what we know of transport, um, by having it designed this way, it can reduce that diffusion distance. Because as we know, according to Fick's law, by reducing that distance that is required for traveling, then it can increase the flux. And so when that happens, then you know that you're going to be able to have a scaffold that's much more efficient and much more likely to have those to fulfill those transport requirements that's needed. So for future directions for what it is that um, can happen in the future, these are just some things that can come out. So smart scaffolds, these can be future scaffolds that can directly immediately respond to transport needs in real time. So for example, they can release oxygen if it needs to, if it reaches a certain acidity level, or if it reaches a certain catalyst point where maybe then a catalyst is released that allows for this oxygen to be released. There's many different ideas and many different ways that this can go. There can be sensors that can be embedded within the scaffold themselves. These can be electrical impulse sensors or something similar, where it's measuring the oxygen and moisture and nutrient levels in real time, so that it's maintaining those homeostasis that balance, so that the skin graft doesn't not integrate, so that it actually does integrate with the rest of the skin. There could be gene activated matrices. They can kind of detect hypoxia and allow for more of the angiogenesis that we want. And yeah, there's many more things that a lot of these scaffolds are going in. It's a very exciting field. But a lot of it is focusing on how is it that we can make sure that the transport of the nutrients and oxygen and everything is required and is there for the skin, because that's just so important. And the goal is to have the skin be as dynamic as possible to replicate the skin. And so just to end off on to kind of wrap this together, in order for the skin graft, in order for the skin graft to survive, that's determined by how well it can perfect the transport in the early stages, right? So the thing is, if diffusion is not perfected at the beginning, then that doesn't really matter too much then if it vascularizes or not, because the diffusion is probably the most important thing for the skin graft. So these successful scaffolds, they can be made, but they have to have that balance between the oxygen, the nutrients, the waste, the moisture, the drugs, all these different things. It has to have that perfect balance because the skin is is a very complex organ. These are our references. And yeah, thank you so much. I did just want to end off really quick because I know that the end of the presentation, there could be questions that could be asked to the students. So I prepared three questions that I can answer right now, as if a student is asking me them right now. So why does thickness matter? Just to quickly answer this. Thickness of the skin graft matters. It's one of the biggest factors for if a skin graft is going to be successful or not. There's many other factors as well, but if the skin graft is too thick in a certain area, or if it's too hard or too dense in a certain area with its thickness, then it's not going to allow for enough diffusion. of certain nutrients and maybe of oxygen. And so this is why, again, repeating about if it's more than the 100 to 200 micrometer region, then that's more at risk of hypoxia and the cells dying. So that's why uh, having it much thicker is usually not ideal. Another question that can be asked is why is diffusion insufficient? So diffusion can sometimes be insufficient if the distances are much longer and if you're not always dealing with skin. So, for example, one of the main properties of diffusion is that it goes very, very slowly, right? Um, and it's very slow and it's very influenced by the concentration gradients around it because that's how it functions. Um, so that's why it has certain deficiencies. That's why you need to be careful that your diffusion is actually happening properly in the skin graft. And then a third question and last question is how does vascularization change transport? So this is a big one because vascularization, when blood vessels are now able to then connect to the graft and connect to the skin around the area, then it kind of it can actually change a lot for the skin graft and it can increase its chances of success because now you have resources, many more resources for uh, diffusion to start from. And the thickness where you could say there's kind of areas of hypoxia, it's going to be lower and lower the more vascularization happens. So it adds more vascularization, just adds convection, right? Because now the liquid is able to transport from one area to another area very quickly, right? So that's actively delivering the oxygen and nutrients much more immediately compared to diffusion. So that's extremely important. But also for this very small distances, for the micrometers, that's where you need diffusion. And that's where convection just can't do that. Um, those are the three questions. And yeah, thank you so much. Those were my slides. And thank you for listening. Take care. Bye.